Hello everyone and welcome to the math crash course for the OpenGL series. I'm redoing this just because I just wanted to make the video a little better. There were a few things that I wasn't so sure on, but now this should be a little more complete. So this math crash course is going to be broken up into two videos. The first one will be on vectors, and then the second one will be on matrices. But once you master these concepts, a lot of the stuff that we're going to be dealing with in future videos with transformations and eventually physics simulation and collisions will be a lot simpler, or you will be able to understand it a lot better. Alright, so today we're going to start with vectors, and the most simple way that we can describe vectors is direction. So they have some sort of direction, and that's pretty much all they are. So you're going to represent a vector x as it's going to be it's a set of numbers, and you can have some number of dimensions, and that dimension doesn't really matter. It will depend on what space you're operating in. So for 3D, for example, we will have three numbers. So for x, it will be x, y, and z. And you can think of this as just the direction in the x, y, z volume. Or if we were in 2D, so x would be just an x and y. And this is some sort of direction. It can represent position, velocity, something else. But you can imagine this or this vector here as the vector from the origin to the point x, y, z. Or I'll do the 2D example right now. So this is point x, y, z. And we have our vector x right there. So that's the vector there. And one thing to note is that this one, like I said before, a minute ago, this vector is only a direction. So if we had another point, say up here, this vector x would still apply here, and it would go to, so let's say this point was 1, 3. This should be actually just x and y. And then the end point of this vector now would be x plus 1 and y plus 3. So the vector itself only represents a direction. It does not care about start points or end points. It simply just will represent the change in a position, or the change in a coordinate. And another way we can represent this is as xi hats plus yj hat plus zk hats. And what these three things are, the I, J, and K with the hats on them, are called the unit vectors. So for our 3D space, I'll get a volume right now. We have our x, y, and z axis. The unit vectors are simply just vectors representing length 1 in each of these directions. So I'll do I hat, which is like this. J hat, or I'll do a different color here, or that's a Z, so that's going to be K hat, and then Y will be J hat, and then each coordinate is now just the multiplication of some magnitude by these vectors. So xi hat represents x units in the x direction. Yj hat represents y units in the y direction, and then k hat represents z units in the k hat direction, or along the z axis. So if we had a point out here, say like this, the vector would be like that, and that would go to our point x, y, and z. And that's if we're using vectors to represent coordinates. You can also use them to represent other things, and we'll get to that later on. So that's essentially what vectors are, at least in the real number space, and how you can represent them in a few different ways. And just as a little extension, you can represent this 2D vector as xi hat plus yj hat, where I hat is in the x direction, so that's I hat, and j hat is in the y direction, like so. So that's cool there. Now we're going to talk about what you can actually do with vectors. So we're going to start with the scalar-vector operations. So we'll just write operations, scalar. So for scalar and vector addition, you're simply going to be just applying the operation to all the elements. So if we had k times x, and I'll just use the x up here in 3D space, this would just become kx, ky, and kz. And then if we did k plus x, you would just apply, this is going to be equivalent to a vector with all elements as k plus the vector x, which is equal to x plus k, y plus k, and z plus k. So you simply add the scalar to each of the elements, and then subtraction would be the opposite of the addition, and division would be the opposite of multiplication. Straightforward there. And a quick note about negation. So if we had k is equal to -1 here, the result would be x is equal to -x, and what this geometrically will represent is the inverse direction. So if we looked at our diagram up here, if we multiplied both our points by -1, so we would have -x and -y, the vector now would just be -x, the opposite direction, exactly the opposite direction. Now, what can you do with these vectors? Well, if you want to do vector-vector stuff, we can do vector addition and subtraction. Let me just rewrite this better. So let's say we have vectors u, which is equal to x1 and y1. I'm just going to do 2D for simplicity. And w is equal to x2 and y2. And I guess I didn't really explicitly say this, but when I'm writing these arrows above the name, that typically will represent a real vector. So anything that has the arrow up here or a bar or whatnot can be represented as a real vector. So now vector-vector addition, we're just going to be adding the corresponding elements. So u is equal to x1, or sorry, u plus w is equal to x1 plus x2, y1 plus y2. Now, let's try representing it in its components. Or so we'll use the I hat stuff. So u is equal to x I hat, or x1 I hat, plus y1 j hat. W is equal to x2 I hat, plus y2 j hat. And we kind of understand now scalar vector multiplication from up here. So, like I said before, this representation is derived from multiplying a scalar by a vector, and the vector is just a unit vector. It's still the unit vector here points to the point 1, 0, 0. That's just the unit vector on the x direction. In the z direction, it points to the point 0, 0, 1 from the origin, and then in the y direction, it points to 0, 1, 0. So those unit vectors are still just vectors. They have special properties, meaning that they have they only go one unit in a direction. So if we want to try adding it this way, and we'll combine like terms, we'll get x1 plus x2 in the I hat direction plus y1 plus y2 in the j hat direction, which then can be translated into our x1 plus x2 and y1 plus y2. So there's more of a mathematical description of how that works, because the u plus w is the equivalent statement of that right there. So these two statements are equivalent. It just, with the component, with the unit vectors, we're representing each component as a scalar rather than just an element in a set. And then subtraction would be the opposite, where you would just do u minus w is equal to u plus a negative w, so which is equal to x1 minus x2 and y1 minus y2, just like that. Now let's try graphically, what would this represent? Well, if we took the 2D example here, and let's say that our first point was out here, x1, y1, and then our second point was over here, x2, y2. So we had our vector u and our vector w, and the resultant point was over here, x1 plus x2, y1 plus y2. Graphically, what this will represent is we're simply going to take the vector w, so I'm just going to copy it, and we're just going to drag it onto the end of vector u. So we're doing essentially a head to tail for the addition. And it would work the other way. If we tried to copy, if we took that and then dragged it onto the end of w, we would get the same exact result. So we're just adding the vectors head to tail, and it will get us to that resultant, to the addition. And then the subtraction, you could just say, well, like I said, it's you add the negatives. So if we were to do u minus w, we would take the negative of w, and then just, which points to minus x2 minus y2, and then the resultant point would be over here, which is x1 minus x2, y1 minus y2, and we'll do the same thing. We will take this, copy it, and drag it over here. The length isn't the same, but it shows it's just for demonstration. And then we'll copy u, and we're gonna drag it like that. So it's all the same there. And you know, if you're looking at this, well, this is a bit beyond the scope of this video, but this seems to be forming a grid. Well, let's say, what if we had a point that was out here? That's like minus 3x1 plus 2x2, and then minus 3y1 plus 2y2. Well, what is that? Once again, you don't need to, this isn't necessary for graphics, but just make you think a bit. Well, this is just equivalent to 3 or minus 3u plus 2w. If you expand out the components, that's what you'll get. And well, let's look at this graphically. You have 1, 2. That distance is not correct at all, but let me make it correct. It's like that, and then 2w up would be, and that's kind of cool, but we're not going to worry about that right now. That's just food for thought if you want to think about linear algebra a little more. So yeah, that's vector addition and subtraction. Now we're going to do a few other things, but before, there's also going to be something called vector multiplication, and that's defined in 2 different ways. But before we do that, we're going to talk about something called the length of a vector. So often we'll want to determine how far it is from the origin to this point. So essentially, we want to get from the origin right here to x1, y1. Well, how are we going to determine that, and how are we going to represent that? If we're given u and we want to find the distance of u, we're simply going to say the magnitude. So that's represented by a double bar. So the magnitude of u is just equal to the distance of u, or sorry, the distance of 0, 0 to x1, y1, which is just by the Pythagorean theorem, it's just x1 minus 0 squared plus y1 minus 0 squared, which is equal to the square root of x squared plus, or x1 squared plus y1 squared. So you just take the components, square them, and then take the square root of all that. Now, like I said, we're going to want to know this for the distance, but there's also another application of this, and that's called normalization. So I talked about the unit vectors being special earlier, not only that they go one unit along a certain direction, but their magnitude is also just 1. And that's what makes them so special in being able to represent vectors as a linear combination of these vectors, because we can say x times I hat, and we know that we'll get a vector. So if we just had, so I'll go back down here. If we said x is equal to x times I hat, we would know for a fact that the magnitude of x is equal to x. Here I'll just say this is equal to a I hat. We would know for a fact that the magnitude of x is equal to a. And how do we know that? Well, if the magnitude along the vector, the unit vector I hat is 1, well then this is simply just a times that vector. So this is equal to a times the magnitude of I hat, which is equal to a, because I hat is 1, and you can verify that using the formula up here. But it's pretty trivial because I hat only has x1 as 1 and y hat is 0, so it's just the square root of 1 of the square root of 1 squared. But so for normalization, essentially what we're going to want to do is we want to normalize vectors so that their magnitude becomes 1, so we can use them as their own unit vector. So if we wanted to transform x, which is equal to, now I'll say AB, or ABC rather, I'll do that. This is or let's say y is equal to ABC, and we wanted to find a y hat, a unit vector along. So if we had our volume, and we had our point ABC, let me just draw this, or yeah, I'll just keep it in black for now. So this is y, the vector y, and we wanted to use this as some direction for some reason. We will use this definitely, but we wanted to get a vector along that's parallel to y that has a magnitude 1, and we'll call it y hat. So that's the unit vector along the vector y. So unit along y. And all we're going to do here is, well, if we know that the magnitude of y is equal to the square root of a squared plus b squared plus c squared, if we wanted to keep the vector y, the unit vector along this direction, but make its magnitude 1, this would have to become 1. Well, how would we do that? Well, if we go back to scalar vector multiplication up here, you would see that k times the vector x is simply just k times each of the components, but it's still along the same direction, x, y, z, because it's equal to k times x, y, z, which is essentially a scaling. So it's along the same direction. So we're essentially trying to find a scale factor. So y hat is equal to k times y, such that the magnitude of y is equal to 1. Well, from this equivalence, or sorry, the magnitude of y hat is equal to 1. Well, from this equivalence, we know that the magnitude of y is equal to, so magnitude of y is equal to, or we'll say magnitude of y hat is equal to k times the magnitude of y, the vector. So this is equal to k times ABC. And if we plug in some numbers, the desired magnitude is 1. And this is equal to k times the square root of a squared plus b squared plus c squared. And therefore, k is equal to 1 over square root of a squared plus b squared plus c squared, which is equal to 1 over the magnitude of the vector y. So all we're doing now is, when we put this together, we see that the unit vector y hat is equal to the vector y over the magnitude of y. So we have found a factor that can normalize a vector to find a unit vector along that original direction. So that's normalization. Pretty cool. Next on the list is our vector-vector operations, which we will have as so it's going to be, vector-vector multiplication. So let's say that we have, and we'll do 3D, so u is equal to x1, y1, and z1, and w is equal to x1, y1, x2, y2, and z2. So we're going to define two different products here. The first one is the dot product, denoted as u dot w. And the way this mathematically what this represents is, so u dot w is just equal to the sum of the products of each component. So we're going to say x1 dotted with y1, x1 dotted with x2 plus y1 dotted with y2 plus z1 dotted with z2. And we can see this just kind of, if we do the column layout here. So a few notes about this, about the dot product. Mathematically, that's the representation. Geometrically, what we're going to see is that if we have some vector w, or u, and then some vector w, the dot product is essentially going to find the parallel component. So this magnitude right here will be the dot product of u dotted with w. And more geometrically, if we put an angle theta here, what this will be is, so u dotted with w is equal to, if we look at some angles here, some trig identities, we'll find that it is u, the magnitude of u times the magnitude of w times cosine of theta. That's just some trig identities there. Now let's do something interesting. Let's take this dot product, this geometrical representation, and let's try using two vectors that are perpendicular. So theta is equal to 90. Well then, u dot w is going to be proportional to cosine of 90 degrees, but cosine of 90 degrees is just 0, so this is going to be equal to 0. So what we can say now is, generally, if you have two vectors that are perpendicular to each other, that are orthogonal to each other, their dot product will be 0. And another application of the dot product is, let's try dotting the same vector to itself. So u dotted with u. What we'll get is it's going to be x1 squared plus y1 squared plus z1 squared, and you can just get that by looking at the components and multiplying them by each other. So this is just, I'll write it out actually, x1 dotted with x1 y1 z1. If you take these two components and just multiply them and then add the products, you will get this. Now what is this? This is what we have found as the magnitude of u squared. And you can also get this from the geometrical representation. This is equal to the magnitude of u times the magnitude of u. So if we just use this geometrical formula, plugging in u as w, times cosine of the angle between u and u is just 0, because they're parallel, so times cosine of 0. Cosine of 0 is just 1, so this is equal to the magnitude of u squared. Okay, let's go one step further. Let's go back into 2D. Let's say we have our vector u is equal to xy, or x1, y1, and I'll just do its unit vector components, so x1 i hat plus y1 j hat, and w is equal to x2 I hat plus y2 j hat. if we take the dot product of these, let's try just writing out the multiplication. So u dotted with w is equal to x1 I hat plus y1 j hat dotted with x2 I hat plus y2 j hat. And if we kind of expand this multiplication here, what we will find is that we're going to get x1, x2 I hat dotted with I hat plus x1, y2 I hat dotted with j hat plus x2, y1 I hat dotted, I hat dotted with j hat plus y1 dot times y2 j hat dotted with j hat. So let's simplify this a little bit. Let's use what we found in the last two things. So the magnitude of a vector dotted with its, or the result of a vector dotted with itself is its magnitude squared. So let's simplify those. So I dotted with I just becomes the magnitude of I hat squared, which is equal to 1. And the similarly for j hat. Now what about I dot j? Is there anything special about these two vectors? If we look at our 2D plane again, this u and w here, when they're perpendicular, that kind of looks similar. The unit vectors I hat and j hat are perfectly perpendicular, so their dot product will be 0. So we're going to get a 0 here because I hat is perpendicular to j hat. So now if we simplify, we get x1, x2 times 1 plus y1, y2 times 1, which is just equal to x1, x2 plus y1, y2, which now we have recovered the original dot product formula, which we put over here, just in 2 dimensions. So that's kind of another mathematical proof of that, but we're still using the dot product and just the geometrical representation. Okay, so that's the dot product. Once again, big thing you need to remember is that you can get the parallel component of a vector to another. Now, second product is going to be the cross product, and it's going to be u cross with an xw. And what this is going to mean is that it's going to, we'll first talk about the mathematical, or here we'll talk about the geometrical meaning first. So if we have two vectors u and w, the cross product of these two vectors is going to get the vector perpendicular. So if these two vectors u and w are in the plane, then the cross product will be coming out of the plane. And how do we know that that's perpendicular to both? And it's a good thing to know that this cross product can only happen in 3 dimensions explicitly. So u cross w, then we're going to say that the cross product will be here. Kind of a crappy drawing, but I'm going to draw it that's a really crappy drawing, but the vector will be perpendicular to them. Now, another thing that you can think of here is, well, what about the unit vectors? If we take their cross product, what is it going to be? Well, if we take I hat cross j hat, what is this going to be? Well, what's perpendicular to both x and y axes? It's just going to be the z axis, so k hat, right? And then j cross k is equal to I hat, and k cross I is equal to j hat. And then another thing to note is that if you go in the other way, so if we do j cross I, you're going to get the opposite. So j cross I is equal to minus k. K cross j is equal to minus I. And then I cross k is equal to minus j. Well, how do we know that that it's going to be a negative? Well, there's something called the right-hand rule here. So in essence, you so we're going to find the direction with the right hand rule. So you're going to put your thumb along V. So you're going to take your right hand. I swear to God, if you take your left hand, I'm going to lose my shit. I've actually done that before, and I got a few physics problems wrong because of that. But you put your thumb along the V, the vector V. Your fingers, your 4 fingers. So you put your hand out flat. You put the thumb along V, your 4 fingers along W, and then your palm in V cross W. There is a lot of noise outside right now. I'm not sure if you guys can hear it. I'm going to try and draw this right now. So if we take our hand, and that's our pinky, that's our ring finger, middle finger. My artistic abilities are on full display right now. Pointer finger and your fat thumb. And your nails are on the other side. And you have really pointy nails. So those are your nails. This is your palm. The vector V is going to be here. Vector W is along your fingers. And then your palm points in the direction of V cross W. And I'm using the dot to represent out of the plane, and a cross would be into the plane. So if it was the other way around, where your thumb was over here, that's another great hand. And this was W, your palm would be on the bottom, so you have all your veins on this side. Then V cross W would point into the plane, or into the screen. And just as a quick exercise, you can try and take an extension of the cross product into 2D by, so in 2D, I said the cross product is not defined, and it is not defined. But in 2D, what we can say is that U is equal to X, Y, and 0. So in the XY plane, the Z coordinate is always 0. And W is equal to X2, Y2, 0. And we would find that, well, I'm going to prove this mathematically right now, but we're going to find that the direction is going to be in the Z direction. But the magnitude is, well, we're also going to talk geometrically about the magnitude. So if we have these two vectors here, so V and U, the magnitude of this is just going to be the perpendicular component. So instead of it being the parallel, so this was U dotted with W, well, this here, that is going to be U, the magnitude of U cross W. Okay, so yeah, it gets the perpendicular component, which we can say is U, the magnitude of U times the magnitude of W times sine of theta. So this is the exact opposite. This is the other leg of the triangle as the dot product, which was magnitude of U times the magnitude of W times cosine. So we just get the other leg of the triangle. So yeah, that's in 2D. But now let's look at the complete mathematical definition of this. So we're gonna have that, or U cross V, and we're looking at the XY, the X1, Y1, Z1, again, the 3D vector. What this is going to be is the determinant of a matrix. Well, we haven't done matrices yet, but I'm just gonna talk about this now, where we have the unit vectors on the head of the or on the top of the matrix, and then x1, y1, z1, and then x2, y2, z2 in the third row. So this is the determinant of I hat, j hat, k hat, and u is the second row, and v is the third row. And if we evaluate this determinant, we're going to find that I hat, or if we take the determinant, it's okay if you don't know how, but essentially we're going to take the top, we're going to expand across the top row, so it's going to be I hat times the determinant of this little sub 2 by 2 matrix, and the sub 2 by 2 matrix is pretty simple. It's going to be y1 z2 minus, so we take this first diagonal product and then this second diagonal product, so minus z1 y2, and that's in the I hat direction. Now let's go for the j direction, and we're gonna, now that we're doing the second element, we're gonna subtract, so it's minus j hat, and instead of taking the sub 2 by 2, we're going to take a different one, which will have x1 x2 as its first column and z1 z2 as its second column. So it's x1 times z2 minus z1 times x2, so once again the diagonal product is still there, and then for k hat it's going to be plus k hat x1 y2 minus x2 y1, and so that's the dot product in 3D. That is the fully expanded one. And now you can see why for in 2D, if we have these two vectors u and w where it's x, y, 0, these z components are going to vanish. So for u is equal to x1 y1 0 and v is equal to x2 y2 0, u cross v is equal to the determinant of I, j, k, x1, y1, 0, x2, y2, 0. And if we expand this, we'll find that the I hat goes to 0 minus 0 because it's a y1 times 0 minus a 0 times a y2, minus j hat, 0 minus 0 for the same reason, but then plus k hat for x1, y2 minus y1, x2. So that's in the z direction. So this is equal to something in the z direction, which is the proof of how that works. And then if you want, you can do an experiment for yourself. Since the cross product finds a vector that's perpendicular to both u and v, try using this expansion here and then taking the dot product. So take u dotted with u cross v, and what you should get is that since these two vectors, since u and u cross v are perpendicular, you should get that this is 0 because u is perpendicular to u cross v, and v dotted with u cross v is also equal to 0 for the same reason. And that's actually how this this expansion was derived, using the determinant. But we're not going to talk about the derivation of that. But yeah. So that is the cross product, and that's everything I wanted to talk about vectors. So in our graphics world, we're going to use vectors to represent positions, velocities, and any physical quantities that require 3 dimensions. So we'll use to represent positions of fragments, also different colors too. You can use a vector to represent RGB as a color. You can use it to do accelerations, velocities, because those have x, y, and z components. There's a lot of other stuff too, but this will really come into play when we start talking about matrices in the next math crash course. So yeah, I hope you guys learned something, and the next video will be on matrices. So I'll see you then. Have a good one.